Dear ladies and gentlemen, welcome in the presentation Repair Connection with Wooden Wedged Dowels, Preliminary Experimental Laboratory Tests, and FEM Model for the description of the mechanical behavior. I am Perria, and with this video I'm going to bring you through the first results of our research project Wedged Dowels. The presentation starts with a motivation for the research. It follows our methodology, the results, and finally the outlooks. The ICOMOS Charter of Mexico is a worldwide reference document for the conservation of timber architectural heritage. This document explicitly asserts that the intervention on traditional and heritage timber structure must follow traditional carpentry techniques or compatible modern materials and techniques. In this document, it is specified that traditional wood-wood connections must be preferred, when possible, with the aim to protect the material authenticity and integrity of the building and to guarantee the principle of reversibility and minimum intervention. On one side, wooden nails based on historic examples continue to be used to secure the position of the half timber joints in one-to-one replacement of historical connections. On the other side, when it comes to replacing damaged timbers where historically no connection was in place, we have to face a different situation. In these latter cases, metal fasteners are used very often, especially if the repair has to be designed for tensile stress structural elements or if a clamping effect is required. In these cases, the choice of the metallic mechanical fasteners is almost unique, because there are no basis for calculation for alternative techniques or alternative mechanical fasteners. However, these latter fastening techniques are not to be favored from the point of view of monument preservation's principle for the conservation of wooden built heritage. With this motivation, we develop an alternative repair connection with wooden wedged dowels as mechanical fasteners. To introduce our new and alternative repair method that meets the demands of monument protection, we just show it on this slide. As you can see in the picture, a wooden wedge dowel consists of a dowel implemented with two wedges inserted in the two grooves on the front and end faces. These special fasteners can be installed in any kind of carpentry connection shaped in a traditional way. Wooden wedge dowels have been used since decades for repair of timber elements together with common wooden dowels from some regional carpenters. The development of the wood wedge dowels was prompted around the year 2000 by local surveying of damage to half timber facade caused by the use of various repair measures such as plastic-containing spraying and filling compounds, moisture barrier mortars, and metallic fasteners. These connections with wooden wedge dowels represents a wooden alternative to metallic screws and bolts or other kinds of repair methods that in presence of moisture can be potentially dangerous for the timber elements and cause damage. The wood wedge dowels can be used for the repair of historical timber elements loaded to axial compression of tensile stress, as well as for structural elements that need a clamping effect. Now follow our methodology. With the aim of the determination of fundamentals of mechanical properties for the wooden wedge dowels, we analyze first existing mechanical models and approaches to classical wooden nails and dowels. On the other side, our methodology focuses on the analysis of selected existing built examples of wooden wedge dowels with the final aim to define geometry requirements, suitable wooden pieces, spacing among fasteners, edges distances, etc. Regarding the existing literature, a suitable mechanical approach for dowel-type fasteners in axial tensile loading has not been found. On the other side, for the development of evidence for wedged dowel type fasteners under axial shear loading, the model from Blas et al. 1999 is a suitable modeling approach. This model approach was also taken as a basis for the verification of wooden dowel type fasteners under shear stress in the SEA 269-5 of 2011. All the results were resumed afterwards in a requirement matrix. In order to adapt the already existing models for wooden nails and dowels for the wooden wedge dowels, further important constructive and static parameters were analyzed in the preliminary experimental investigations. Furthermore, a FEM model of the fasteners was developed. At the end of this process, all the collected parameters were implemented in a final requirement matrix. Some of them were considered a fixed parameter and some other parameter as variable. The variable parameters in the requirement matrix are represented on these slides and were analyzed and combined in the specimen of the experimental campaign. The first parameter or variable is the combination of timber species. The chosen combination were first of all H1, softwood hardwood, and the second combination was A2, hardwood for structural components and dowels respectively. The second variable parameter is the angle phi between the orientation of the groove on side 1 and fiber's direction in the building component on side 1. The angles 0, 45 and 19 to the fibers were considered. The third variable parameter is the angle beta between the orientation of the groove on side 1 and groove on side 2. In the combination G1, you find the orientation of the groove on the side 2 is parallel to the orientation on the side 1. In the combination G2, you can find the orientation of the groove on side 2 perpendicular to the orientation of the one on side 1. The objective of the experimental campaign tests are the following. First of all, the analysis of the distribution of strains in the material when the wedge is inserted into the groove. Second is the analysis of the risk of fracture and cracking in the materials of the dowel and building components when the wedge is inserted into the groove. Third is analysis of penetration depth of the wedge in the groove. Fourth, calibration of decisive geometric constructive parameters and determination of some manufacturing rules. Finally, the collection of data on the strain behavior of the materials for the development on the FEM model for the wooden wedge dowels. On this slide, we show the test steps. In the first stage, the dowel is installed in the pre-drilled building components that simulate an half joint to connect them. In a second step, the test is started. The wedge was not introduced, as in real conditions, by means of a hammer. The reason is the attempt to repeat for every specimen the same boundary conditions: velocity, load amount, direction of the load, without natural directions corrections of a human operator, and centered load on the wedge. The wedge is inserted in the dowel's groove by means as a universal testing machine, as represented in the video, with a strain control test, velocity 1 mm per second. The wedge is introduced in the groove up to the fine failure mode, buckling of the wedge in the most of the cases. The superficial, visible and non-visible deformation strain during the test were recorded with an optical measurement system, as also shown in the picture below. All the collected information about the strain of material were used to shape the FEM model. On this slide, the two most significant failure modes are shown. On one side is represented the cracking of surface of structural member. On the other side is represented the cracking along dowel's core. In this slide are shown the results divided for wood species combination and combination of parameters. For the wood combination H1 with structural elements in softwood, was shown that both the configuration T245 and T219 perform well. The configuration T245 shows just 14% probability of cracking on the surface and 21% probability of cracking in the dowel. The combination or configuration T219 shows the highest probability of cracking in the dowel with 68%, but on the other side, no cracking probability on the surface. The configuration T20 shows very different result. T20 showed a very high risk of cracking both in the dowel and on the surface of structural member. For this reason, this configuration was excluded as a suitable geometric constructive combination. On the other side, on the line underneath, the wood combination A2 with structural element in hardwood is shown. Here it showed that all the configurations present low probability of cracking both in the dowel and on the surface of structural member. Therefore, all three configurations were considered as suitable geometric constructive combinations. Finally, the FEM model results are presented. The simulation in the FEM program were calibrated on the basis of our optical measurement as shown on the left side. For the modeling were adopted two main hypotheses. First hypothesis is that the action in the test is for us an interpretation of the action of introducing the wedge in the groove, represented in the model by volume displacement. Second hypothesis is that the action neglects the presence of friction and imperfection on the contact surface between wedge and dowel. Furthermore, the material properties for building structural component and wedge in the model were calibrated through an iterative process based on material unknowns and the optical measurements results. Finally, material unknowns were assigned in the first simulation series on corresponding wood classes according to DIN EN 338. The calibration on the FEM model was done by comparing the optical measurements and the results of the simulation of selected test specimens. In this case, test specimens of the shown diagram is at A2 T10 T290 G1. In the first diagram on the left side is shown the piston displacement and deformation perpendicular to the fibers on building component surface. In the second diagram in the middle is shown the piston displacement and deformation parallel to the fibers on the building component surface. In the third diagram on the right side is shown the piston displacement and deformation perpendicular to annular rings on dowel's cross-section. The agreement between the test and simulation is the best possible up to a displacement U equal to 0.7 millimeters. Above this value, the idealized elastic-plastic ratio of the model, of the FEM model, does not take into account the loss of energy after failure, and therefore the diagrams diverge. About the behavior of the dowel in the last diagram is on the other side a continuous agreement also above this threshold. Finally, the FEM model results are presented. In this first slide I represented the global deformation and the global stress in the dowel as simulated. And in this second slide is shown the agreement between the simulation of the strain in the building component and the picture of a tested structural member on its surface. To conclude, the current paper represents the first result of mechanical behavior of wooden wedge dowels. After the analysis of cracking in the structural member and the wooden wedge dowel, some determinant geometric constructive parameters of the repair connection were defined. The next step of the investigation are, first of all, the determination of the influence of the geometric constructive configuration on the load-bearing behavior and load-bearing capacity. And second, the development of a mechanical model of the load-carrying capacity of wooden wedge dowels under axial shear stress and axial tensile stress. We would like to acknowledge Zukunftsbau and the German Ministerium BBSR for the support to our research.